All right, I am now officially recording. Thank you, Harmon, for reminding me of that. All right, so that pen is dead. So next pen. So this, let me kind of repeat a little bit of what I said without where I wasn't being recorded. So again, this lab is a second of two labs that are on Chapter 18 material. This week is officially Chapter 19 for lectures. Chapter 19 is on electrical potential energy and electrical potential. Next week is Chapter 20. That's on electrical circuits. So we actually talked about. I had to divide. And by the way, I had to divide the lectures into two parts. The last hour, 55 minutes of the previous lecture became garbled, I think, because of a thunderstorm that flew over. And so I had to redo that. And so the second part is really a redo of the last 2 hours of the previous lecture. For some reason, the redo became 3 hours. I'm not really sure how that happened, but anyway, so toward the end of the chapter 19 lecture, we actually talked about the first circuit element called a capacitor. Very important. So watch the entire lecture. In chapter 20, we'll talk about our second of three circuit elements that we're going to talk about in this class, and that's called the resistor. If we were meeting face to face, we would have already started putting together circuits. We would have already started without even the chapter 20 lecture. We would have already started putting together resistors, which kind of drove me crazy because, you know, before I even got to electrical circuits, I had to go and talk about it, you know, in the lab without actually going into the theory. So here you were, first week of class, talking about circuits, and we hadn't even talked about electric fields, electric charges, or anything yet, right? So anyway, at least we're not going to have that problem, the cart before the horse. We're always going to have our lectures before we have the lab that covers the lectures. So that's the way it's supposed to be done. So anyway, in chapter 18, you know, we talk about Coulomb's law, and so the idea is we know that there is a charge of interest. In general, you want a charge distribution, right? So this is the problem they really want to solve. In general, there's going to be some sort of distribution of charge. Call it rho of R. Okay, and we want to ask the following question. We want to say, I want to know at some distance R away, some location in space at some R away, some vector R. I would like to know what the electric field is right there. I want to know what the electric field is. Now, and that's for a generalized charge distribution. We realize that the answer to that question is Gauss's law. And again, Gauss's law is discussed in chapter 18. That is how you, in general, answer this question. You know, that's in general, that requires integral calculus. I mean, Gauss's law, officially, if I remind you, I mean, if you take the surface area of a charged object, you divide into little tiny areas, and of course, in physics, an area is a vector. It's specified by an area normal. So if I have a little piece of area, the area normal, which I'll call A, the direction, and the normal is a fancy word that says perpendicular to a surface. The area normal would be an area, magnitude would be area like you normally use, the length times width, but in a direction normal to the surface. And so what you want to do is you also want to look at the electric field everywhere. And say there's an angle theta. So you're going to be adding up all these dot products. So Gauss's law basically says that you're going to add up all across the area. That, you know, you're going to make the area so small there's only one electric field vector going through that area. You take the dot product of E sub I dot A sub I on the left, all these little dot products. And on the right side is nothing more than the charge enclosed. And again, you always want to be drawing what's called a Gaussian surface. You draw this little skin over your object. It's a three-dimensional skin, essentially. We call it the Gaussian surface. And you integrate, or essentially you add up all these E sub I dot A sub I's, and it's the charge enclosed in that Gaussian surface divided what's called the permittivity of free space epsilon naught. So that's Gauss's law written in the college physics speak. But again, what you really want to do, you want to do it perfectly. You make the areas become differential areas. Then this summation, so summation over I in this case, the summation becomes adding the calculus way, and that's the integral. So essentially, in Gauss's law, you have to do what's called a surface integral of E dot dA. You have to add up the dot products infinitesimally of all vectors over a Gaussian surface, and the right-hand side stays the same. It's a charge enclosed over epsilon naught. So essentially, what Gauss's law tells you in general is when you get done doing this calculation, this calculation is most easily done if you are talking about high symmetry situations. But in general, this is a very hard integral to do, and again, you can only really do it, really well for in symmetrical situations like the parallel plate, like parallel plate capacitor, or with spheres or cylinders, things like that. So unless you have a really nice situation, that's what you can do. But what you get though is in general, you get a relationship is electric field in terms of some functional with respect to the radius. And that's the answer that I want. I want E as a function of R in general. And so I can always get it by using Gauss's law. But the problem is, most of the time, Gauss's law is too hard to do. You have to be taking graduate level electromagnetic theory to have a chance and be able to do this. And so what we start off with is we have a couple of charge distributions that we do know. One of them is, instead of having this charge distribution, we can just have the charge of interest as a point charge. So what do we know how to do? Well, we know how to do a point charge. Okay, I don't need Gauss's law for that. In fact, we didn't even know about Gauss's law, and when Coulomb did this, Coulomb said, okay, well, I want to understand a point charge. That's my charge distribution now. It's a point charge. Now I'm going to pick some area out in space, but what I'm going to do is I'm going to put a test charge there. I mean, this is going back to Coulomb. I'm going to put a positive test charge, and I know there's some sort of a distance r. And through very, very careful calculations, Coulomb found that the force between these two charges, the charge of interest and the test charge, again, this is a positive test charge. Test charge is always positive by convention. And we come to find the force is a constant K times the product of the charges, the test charge times the charge of interest, or the source charge, as oftentimes people call it, divided by r squared in the r hat direction. R hat just means it's along a line along r. This is a pointing vector. This is a unit vector, as it's called. Has a magnitude of 1, and all it does, its whole job is to point that way. So along a line between the two charges, from center to center. So again, this is a law that for point charges. Again, this is only good if the charge distribution, and we're always asking what's charge distribution, is as simple as possible. Is a point charge. It's going to be positive or negative. That's when this is good. Okay, you can't use it for any other kind of system. Well, here's the issue: is that we have a physics quantity or a calculation that depends on how I actually did the measurement. If I ask you, I say, hey, can you tell me what your temperature is? And you're not going to tell me, oh, it's my temperature is 98.6 degrees Fahrenheit using the thermometer I bought at CVS Pharmacy, or 98.6 degrees Fahrenheit using the thermometer I bought at Walgreens. You're not going to tell me something like that, and I don't care. I shouldn't have to care that you're using a thermometer from Walgreens or Walmart or CVS. The way you took your measurement doesn't matter. All right, and so here we have a situation. Here we have a formula where the way I took the measurement, this test charge is like putting your toe in the bath water to figure out the temperature of the bath water. This test charge, if I'm talking about your temperature, I don't want to know about your toe, or I don't want to know about the thermometer you used. So I want to divide out how I took the measurement. And so when we have this concept of an electric field, we say, well, there is an electric field emanating from this point charge. And I can know about this electric field by putting a test charge and seeing what happens to it. So I have this concept where I say, well, I have an electric field, and I define it like this. I say that the electric field is defined as the electric force. Let me put a little E on subscript on the force to remind ourselves that it's electric, it's not gravitational or any other way. It's electric force divided by the test charge. I want to divide out the test charge. I don't want the test charge. I'm going to divide it out. This is called the electric field. Now, what are the units of electric field? Well, newtons per coulomb, or as I proved in one of the early problems in chapter 19, you can actually also refer to it as a volts per meter. They're perfectly equivalent. And I proved that working out a problem in chapter 19. I don't want to do it again, but look in the video of chapter 19 or early on in the video, you'll see how I proved in one of the problems that a newton per coulomb is the same as a volt per meter. They're the same. So I have this concept of electric field. And so, okay, well, that's in general. This is in general, you know, whatever, you know, you have some electric field that's out there, however it got generated, whether it's from some generalized distribution of charge or whether it's from a point charge, I don't care. The fact is, the electric field is going to be whatever the force is felt by that test charge divided out the test charge. That's your electric field. And so, okay, well, what would the electric field be for a point charge? Well, for a point charge, real easy. I told you electric field is the electric force divided by the test charge. Well, that's going to be, you know, basically divide out little q. It's just going to be K cap Q over R squared R hat. That is electric field for a point charge. It tells you that I divided out the test charge Q. I don't care about it. And what it is electric field is directly proportional. It's a vector. Again, it's a vector along the radial. Wherever I might be taking, taking a measurement, whatever radial, it is either radially outward or radially inward. It's directly proportional to the magnitude of the source charge and divided by the center to center distance squared. Again, this is only true for a point charge. There's electric field for any charge distribution. I'm lucky enough to be able to actually know Coulomb's law and be able to get this very easily for a point charge without having to go through Gauss's law. In general, I have to go through Gauss's law. In general, getting an actual formula for the electric field is very, very hard. And I can't just do it. That's very easy here, but that, again, remind you, this is the simplest possible case. We're crawling before we walk. This is the point charge, all right? And so that was what this lab is about. We're talking about, so half of this lab, part one, is about looking at the electric field of a point charge. Now, again, it's not electric force, it's an electric field, all right? And then the second part of it is going to be talking about what's called an electric dipole. And I think I'll go through the lab for part one, then we'll give a little dipole lecture, then we'll go through the lab for part two. I don't want to inundate you right now. Let's just kind of concentrate on one thing at a time. All right. So if you look at the bottom of page one on the lab, okay, so we don't really do anything with the simulation software quite yet. We wait until we kind of have to kind of do a little thinking from our understanding our lectures. And so again, that is the electric field. So let's kind of take a look at what we expect the electric field to look like. So we have this concept of electric field lines. And again, I'm not going to go too much into electric field lines. I mean, I do a lot of it in the chapter 18 lecture. So please do watch it. I mean, everything you need to know about physics is in those lectures. All right. So please do take the time. I take the time to make the lectures. Please take the time to watch the videos. So we have, as I said, the electric field for a point charge. Again, we're looking at a point charge. So what does it look like again? It's going to be this K, the source charge divided by R squared in the R hat direction. Remember that K is 1 over 4 pi epsilon naught. Epsilon naught is the permittivity of free space. All right. And so that's a special constant of the universe. We wrap this all together. This combination happens so often, we just call it K. All right. So what does this look like? Well, if the point charge, and again, let's remind ourselves, remember, we're talking about positive test charge. So the electric field is defined with respect to a positive test charge. What does it do to a positive test charge? Well, electric field is going, the idea is it's going to push out. The test charge is going to go along or the direction of electric field. So the idea is the test charge, positive test charge, let me be more specific. Will move in the direction of the electric field. So that means that we know from Coulomb's law, and we know from the experiments of, like, for instance, the glass rod and the silk cloth, that positive test charges, like charges, repel. So if an electric field, if I have a charge that's going to emanate an electric field that's going to drive a test charge away, that would be the behavior of a positive source charge. All right, and so if the source charge is positive, then that's going to cause electric field lines are going to be radially outward. So if Q is positive, the electric field lines will be radially outward. That's their direction. Okay, so this is the rationale here. So I see something like this lab, and I see this on the bottom of page 1. I see a grid, and I want to try to draw out what things look like. Well, I should very carefully try to draw something like this. I have an axis, another axis, and I should be. If I imagine Q being positive, say Q is positive, the electric field is going to be radially outward. I might label this the x-axis, label this the y-axis. This is my electric field. These radial spikes everywhere. Should be the same length if I drew my picture well. Radially outward electric field. And I can just say, well, yes, I understand it's dependent on R. Well, I can say, well, I know that R is equal to the square root of x squared plus y squared. How do I get R if I know the Cartesian coordinates? I get it from the square root of x squared plus y squared. That's the Pythagorean relation. If Q is negative, if the source charge is negative, well, that's going to want to pull a test charge toward the source charge. So electric field lines will be radially inward. So instead of having these arrows outward, I'll have them inward. So the picture I drew was the first picture. On the bottom of page 1, I very carefully drew a picture. that look like the first picture with a positive test charge, positive source charge, positive source charge, and I just drew about 6 or so very carefully drawn radially outward electric field vectors. That's all I did. And I stated that R is equal to the square root of x squared plus y squared. Because I drew them in Cartesian coordinates, but it really is radial. And how do you get to the radial coordinate? Well, if you know x, you know y, you get R through Pythagoras. All right, and so again, I could draw this at any radial, it's going to be the same. It's isotropic, it's in all directions the same. It's a big fuzzball, basically. Okay, that's bottom of page 1. Any question about that? All right, I'm on page 2. I'm on the top of page 2. All right, so we're going to start looking at the simulation now. All right, that's the theory. I'll get back to, I'll end up writing on my whiteboard more, but let's get to the actual simulation software. I mean, that's all I really have to say about point charges. I mean, it's Coulomb's law and getting electric field from Coulomb's law. All right, so now let's go to, you know what, I brought up the actual Word document, but I never actually opened up the lab. All right, here we go. Open up the software. Let me get to a point and I'll start sharing my software, the software with you. I don't know what it is. Zoom really slows down everything. I usually try to bring this up before I bring up Zoom, and I ran out of time. I think it's coming up. Any questions in the meantime? While I'm waiting for the software. Oops, I didn't bring it up twice today. All right, here we go. So I'm going to fire it up now. All right, I'm loading. I'll share my screen in a moment. All right, screen share time. Okay, you should see a black screen, and so really what we're going to do is we're going to do the simulation and very much set up situations where we'll start off with setting up point charge, and then we'll end up setting up what are called dipoles. So as I read number 2, and again, I want you guys to do this also on your own, but open up a simulation, activate the grid. All right, very simply, you click the little grid box. Now I have a grid. Place a 1 nanocoulomb positive red color charge on the grid. So I'm going to stick the 1 nanocoulomb charge someplace. Let's maybe stick it like right here very carefully, maybe at a grid intersection. And you'll notice that the moment I lay it down, it's going to show you the radially outward electric field. And you notice that the electric field, the closer you are to this 1 nanocoulomb charge, the greater the electric field strength is. I mean, you see that by the length of the vector, and they're all radially outward. As the vector moves further and further away, the length, the magnitude gets smaller and smaller. And again, it's because of the 1/r² relationship. The charge that we just laid down is our capital Q. Okay, so you read on, so this is sometimes called a quote unquote source charge. It says it's a source electric field. we are going to measure. To make a measurement of electric field, grab an E field sensor and place it where you want to measure the electric field, all right? So if I grab a sensor out of here, so I have my little sensor, and let's just say I stick it over here. Now each of these grids is a half a meter. So half, here's about a meter away, right? And notice that you'll see a vector that's going radially outward. If I move this point, let's say any other way, if I kind of go around the circle, you notice that it's radially outward. And if I, oops, my mouse is going crazy, sorry. If I go further away, the magnitude gets, as I get closer, the magnitude gets bigger. If I go further away, the magnitude gets smaller, right? And so I can play around with this, and then of course, you know, before you know it, we're not too far along the lab, and we're already being asked questions. So I'm on number 2, the second paragraph. It says, move the sensor around and observe how the electric field is different in magnitude and direction at different locations. Summarize what you observe and how the magnitude of the electric field depends on the location below. I mean, I wrote the closer the sensor is to the charge, the greater the length of the electric field vector, and hence the greater its magnitude. The further away the sensor, the shorter the length of the electric field vector, and hence the smaller its magnitude. I mean, just like we just saw. Closer in, you know, the closer you are to the charge, the greater that length of that field electric field. That magnitude is that length is a statement or a representation of its magnitude. As I go further away, the magnitude of the electric field gets smaller and smaller, right? So again, that's essentially, you know, write down what you just saw. Again, the first part of the question is regarding magnitude. And then it says, summarize what you observe and how the direction of the electric field depends on location below. I mean, we haven't done any experiments yet. We're just playing around. The direction, well, the direction is always radially outward from the source charge because the source charge is positive, right? It's going to be radially outward from the source charge no matter what, because when I test the electric field, it is what happens to a positive source charge if one was there. All right, so a positive charge is always going to be driven away. Electric field is always going to go along. It's always going to drive a positive charge outward. Again, always assume that the test charge, if we don't see one there, always assume that the test charge is positive. And that is a positive source charge as we were directed. It's a positive 1 nanocoulomb source charge. All right, so electric field is going to be radially outward. No matter where I put it, it's going to be radially outward from the source charge. If it was a negative source charge, if I put the negative 1 nanocoulomb charge, we'll do that later. We'll play around with the negative charge. If we did that, we find out that everywhere you look, all electric field lines that you see right now would all reverse, and it would come inward. All right. Okay. Everybody with me? I'm on number 3 now on page 2. Make a measurement of the electric field 1 meter away from the charge scale as shown in the bottom of the screen. Note that the units of electric field are volts per meter, which equals newtons per coulomb. Again, I worked it out for you in the chapter 18 video. Record the value below. So what we're going to do, and we're going to back it up with a calculation, is remember, if you take a look at the, oh, you know what? I need to click the values. There you go. When I click the values, I have a little legend of how big how big a meter is. So a meter, if you look in the very bottom right, a meter is basically, this is across 2 of these grid squares. All right. So if I want a meter away, and I'm gonna make life easy. I'm just gonna go along either vertical or horizontal lines. I'll go vertical here. So let's see here. Here's my location. I'll try to put it on the crosshairs as best I could. Here's a half a meter in a major grid. Here's a meter. So I'm gonna try to very carefully, and I'm not gonna do any Pythagorean stuff or anything. I'm just gonna move it straight along a vertical or horizontal. That way, I can just do a point-to-point measurement. This is, you know, this is of a straight line. So there you go. And again, this is a little bit hard to read. I get about I get about 9.03 volts per meter when I do that. And you're gonna have some error, but I mean, again, that's what I get. Now, so the question then becomes, again, that's hard to read, but that's what I read. I read 9.03. So I'd write in that little space, you know, for instance, 9.03. Again, I would hope that you would, and of course, remember it's volts per meter. And when I did it, I got something different. But I want you, I want you guys to go do it. And I don't really want to see about 9.03 numbers like that. See you guys do it. But anyway, that's what you do. And then you predict the strength of electric field will be at the same point if you double the amount of charge. Well, if I double the charge, let's make a prediction. So if I think that E right there is 9.03, so let me stop sharing for a moment. Let me go back to the theory. I'm going to go double the charge. Let's go back to my board. This is more of a calculation. So if I think that I have a radial electric field and it's equal to 9.03 volts per meter. So this is called, we'll call that E1. So E1 is 9.03 volts per meter. Sorry, it's just an old pen. All right, that's just what I measured. You'll measure something else. So let's see, that accounts for what? Well, that accounts for, you know, again, I have a radially outward electric field. Oops, this is not a very good picture. There's my electric field, and I picked the point. You know, I picked the point there. I'm not going to put a test charge here because but I picked the point that is R away. And this represents what? This represents K Q over R squared R hat. You know, if I double the charge, what should I get? Well, if I double the charge, quite simply, I would get K, well, I double the charge, 2 cap Q over R squared R hat. And of course, I could pull the 2 out. E would equal 2 K cap Q over R squared R hat. And oh, well, by the way, K cap Q R squared over R hat just happens to be what I call E1. So E now is just going to be nothing more than 2E1. So I would expect if I stuck another charge there, I would expect it to be about, what is that, 18.06. Right, that's what I would anticipate seeing. Well, I mean, that's what I would, I would anticipate seeing. That would be the proof that I would do for number 4. Well, number 5 says, well, place another 1 nanocoulomb positive charge on top of the previous charge and measure electric field again in the same place. Record your result below and put the added charge and put the added charge in the charge bucket. So again, I'm going to go back to sharing, and let's see what we get. Let's see if that's actually, if that's what Coulomb tells us it should happen. Let's see if that actually does happen. So that's really easy to do. So number four is that calculation I just did, that derivation and writing that number down. Number 5 is essentially the empirical evidence, if you want to call this empiricism. This is a simulation, but so I'm going to take another 1 nanocoulomb charge and stick it right on top of the original one. Effectively, that's doubling my charge. And what happens now is I see it's 17.9. So I probably didn't put the second charge on perfectly, but 17.9. So I'd write down 17.9. I mean, when you do the experiment, maybe it'll do better than I did. But anyway, I just doubled the source charge. Now I have 2 nanocoulomb, positive 2 nanocoulomb charges sitting on the source charge, and that effectively then doubled my electric field, just like I predicted. Why? Because the electric field of a point charge is directly proportional to the source, or electric field of a source point charge is directly proportional to its magnitude. Double the magnitude, double the electric field. Okay, so that's number 5, basically. You get number 5 from a measurement. So number 6, did your prediction agree? What can you conclude from the dependence electric field on the amount of charge? Now again, when I see something like number 6, I don't want to see the word yes. You know, I want to see yes and back it up with something. Yes, how well? Yes. I mean, you don't tell some, if you're a veterinarian, you don't tell somebody that their dog has cancer and leave it at that. You want to say, well, yeah, I saw this because of this radiological experiments, or I saw it because of this or that. You always want to back up things with evidence. So I want to answer the question. I'll go back to the whiteboard here. I want to answer the question about how well do I know this answer, or how, when I say I did a good job or I closely agreed, quantify what you mean by that. And you always want to quantify and back up everything in physics. So I'm predicting theoretically that I should get 18.06 volts per meter. I just did the measurements. So my E theoretical, I'll put a little T here. My E theoretical, a little T for theoretical. Well, I did the calculation, and some of it's slopped over by experiment too. So again, this is twice an experimental value, but again, I'm predicting that I should get 18.06 volts per meter. Okay. However, I measured it, and I'll put a little M for measured. I measured this value, and I got 17.9 volts per meter. How well did I do? Well, you don't want to do a percent error because you don't know what the scientifically accepted value is. What you want to try to do is a percent difference. So I would kind of back it up by saying, well, I'll calculate percent difference. Why I keep using this pen? Oh, I guess that's right. Percent difference. Mixing up my pens. This is an old pen. Sorry. The percent difference is given by the following. You might have seen this formula before, or maybe you haven't. But in general, if I want to calculate a percent difference, because I'm trying to compare two values. Neither one of them can I call scientifically accepted. I'm trying to compare two values with each other. How basically, not an accuracy measurement. The accuracy would be how well do I agree with this, what I would call the scientifically accepted. I want to actually do more of a precision calculation, which would be percent difference. So I want to do something like this. Percent difference will be the absolute value, I would say, I would call E theoretical. I'll take the hats off and I care about the magnitude, minus E measured. Take the absolute value of that, divided by the average, which would be 1/2 E theoretical plus E measured. So I take the absolute difference and I divide it by the average. So the average is what? Add two things, divide by 2. Again, if 24 of you took an exam, I would add, if I want to get the average, I'd add up all 24 exam scores and divide by 24. Right here, I have two things that add up. Two of these numbers, divide by 2. That's why there's a half there. And of course, I want to make this a percentage, so I want to multiply this by 100%. All right. So how well did I do? Well, let's see here. Percent difference. If I can put this in here. Tell me if I fall. Huh? Tell me if I fall off the board here. I'm gonna do the. Well, let me just. You got this formula. Let me just replace it with numbers. So absolute difference. Well, okay, my theoretical 18.06. Again, everything's volts per meter, and they're all going to cancel out anyway. Minus 17.9 divided by 1/2. 18.06 plus 17.9. Again, you'll have your own numbers. These are with my numbers. Times 100%. And I just measure these values, so I don't have an answer yet, but let's do it. So let's see, 18.06 minus 17.9.
I got 8.8 times 10 to the negative third, negative 3.
Let's see what I get.
0.008898. Oh, times 100%. Yeah, 0.88.
About 0.89%,
Yeah.
roughly. Yeah, you don't want too many digits because you only know it about, I mean, I could probably go 0.8, well, it's 8898, so yeah, all these numbers will end up around each other. So I probably 0.89 is good enough. But again, you see a percent difference, you see an accuracy, that's really doing well. When you're seeing that, that's a statement of accuracy. So I would answer a question like this. I mean, I just did that calculation. I would answer a question. I would answer it in the following manner. I would say the agreement is close. As evidenced by the percent difference calculation, or percent difference of 0.89% as shown. And so again, you did well. Well, how well? Well, this well. All right, you didn't do perfectly, but you did. This is a very, very, very good number. I mean, as far as, you know, if you're doing an experiment, it definitely looks like you know what you're doing. So what this means is that we can conclude that the electric field E is directly proportional to the magnitude of the source charge Q. The onus is always upon you as a scientist to prove. You always got to prove everything you state. Every time you make a statement, the onus is upon you is to back it up and get ready for the arrows, because other scientists will start shooting arrows at you. Do believe me. I mean, you go up to a scientific conference, you got to wear your bulletproof vest, basically, right? So you always have to back up everything you say. So, and it's not like scientists are trying to be obnoxious. They're just trying to make sure that science is done correctly, and that we actually get answers, right? So anyway, that's the kind of answer you'd get with problem 6, right? So again, this is all kind of backing up. Now we're going to do some more experiments. Any question about this? I mean, I just turned the page to page 3. Now I'm going to go back to the software. Here. All right. So number 7 says, now that we want to investigate how the strength of the electric field depends on distance from 1 nanocoulomb charge. Right. So we already investigated increasing the source charge. How does electric field depend on that? We already tested that now. Now we're going to test distance. That's another variable that's in the equation. I mean, okay, so Coulomb claims that it's KQ over R squared. Okay, well, what are variables? I mean, obviously K is a constant, so we can vary Q or we can vary R. All right, so we're going to vary R now. So now we want to investigate the strength of the electric field depends on distance from the 1 nanocoulomb charge. So we want to, so remember we have a positive 2 nanocoulomb charge in the middle. I'm going to pull one of those back into the toolbox. So I'm going to do that. So now I only have 1 nanocoulomb sitting here. All right. So let's remember to do that. Make measurements of the magnitude of the electric field at 4 different values and complete the following table where R is distance measured. So you're going to go with half a meter. So I'm sitting at a meter. So at a meter, we can just grab that value. I guess 9.03 is, or you do it yourself. And for half a meter, I'll do that. And maybe I'll do one more. And then, so half a meter, you notice it gets big. So try to line it up nicely. I pick a vertical so that, I make life as easy as possible. I'm a little bit off center there, as you can see. And you're doing well if you can try to get that red line lined up with the vertical. But again, maybe you can do better than me. That's like 34.9. So maybe 34.9 would be that one. That's at a half. Remember, every major grid square is a half a meter. So I'm a half a meter away from the 1 nanocoulomb charge. That's electric field. Let's say 34.9. And maybe you go out. Okay, here I just did 1 already. So 1. Ooh, that's okay. Hang on one second. He went on vacation. What happened there? All right. Is there a reset? Sorry about that. Yeah, my mouse went crazy. All right, let's go back. All right, so do another measurement. Sorry about that. So I'll stick the 1 microcoulomb charge back to where it was. That was weird. All right, there we are again. And go back to my sensor. So what did I say? 1. Yeah, so let me go. I got 1.5 would be about here. And the vector's gotten a lot smaller, maybe 4.06. Maybe you can do better, but again, you're going to fill that up. So you'll do it for 2 and 2.5. Remember, that's 1.5 because I have 1, 2, 3 measures of grid spacing. Each measure of grid spacing is worth a half a meter. So you'll plot E versus R on a graph. Does your graph show behavior? So I did this experiment earlier, and I'll show you what I got. And so again, I don't want to go make this an Excel class like last time. So I'll kind of show you what I did. But now if you have any issues with Excel, I'm happy to help, of course. So let me go and share my screen again. So my software went away. I'm going to Excel now. So share my Excel. So now we do some data analysis. Sorry. Now I did, like last time, my independent variable is the left column, my dependent variable is the right column. Those are the measurements I got. I slurped up those measurements. I went to insert after I did the measurement. So I'll just kind of do it here. So I have these two hidden, I highlighted. I went to insert. And of course, I went to I went to my charts, and I just hit the scatter plot. And again, I showed you this last time, but scatter plot, you put the axes, you put a title on, so on and so forth. You make you add a couple. You hit the little plus button to add. Axis titles. I even changed the color of the data points just to make them black, which shows that better. And I did all that, and I did when I was all said and done, I did a move chart, and again I did a move chart, and I created a name for my chart. I called it E versus R. I did all that this morning. And when I did all that, I got the following plot. That's what I got. I label it nicely: electric field versus point charge E at a radial distance. Again, R is in meters. Always give your units. Do not put an axis title or a variable without your units. I gotta know what units you're talking about. R is in meters. Yes. Electric field is in newtons per coulomb, or you can put volts per meter. So you see this nice. Now, you might wonder, okay, how did you get this curve? You showed me a scatter plot. Well, remember, I also have the ability to do add trend line. So I added a trend line. Well, add trend line is an option that you had. I already created it. So well, let me bring it back. All right, so I got rid of it. So add trend line. Let's do it again. Oh, I'm sorry, brain not working. Select the data first and then add trend line. Okay, so select the data, then add trend line. There it is. Format trend line, very bottom. Now, last time we tried to format things as linear. This time, we want to actually pick power. Okay, we want a power curve. Power means it's not linear, means that your power is 1. Y equals mx plus b. A power 2 be mx squared, power 3 mx cubed, so on and so forth, right? Well, you expect to get, you have to have what? You actually expect to have the electric field being proportional to r to the -2, right? Because it's a kq over r squared. 1 over r squared is the same as r to the -2. So your power curve, you would expect to have some sort of a constant times 10 to the -2. So I'm gonna select power this time, not linear. And I want to display my equation, which I just had it up, but I erased it. All right, so there's my equation. Let me make it even a little bigger for readability, because I'm older than you guys, so man. Blow this guy up. My mouse is really sensitive today. I don't know what's going on. All right, I'll make this so it's really easy for anybody to read. All right, so my power equation says that y equals 9.0882 x to the -2.037. That's what that says. So I can start answering some questions. So again, I'm going to want to turn a graph that looks a lot like that. And so your number 8 says, plot E versus R. Does your graph show the behavior of the electric field with the distance that's predicted in problem 1? Well, how would I answer that question? Well, according to my data, I would say, I mean, what am I expecting? Well, I'm expecting for like number 8, I'm trying to prove that Coulomb is right. All right. So for like number 8, we expect E to be proportional to r to the -2. That's what we expect. According from the plot, the plot, so the power curve of the E versus R plot gives, I mean, you're going to have different numbers, but it gives E proportional, well, let's just put it this way, it gives E equals 9.0882 R to the -2.037. So E is proportional to R to the -2.037, which shows data that closely matches E proportional R to -2 behavior is predicted. Again, you see it. 2.037 is a great job. I mean, that's really close to -2. It's not perfect, but that's really close. So you'd say something like that in number 8. Number 9, so number 10 actually wants you to write down the power equation. So I would actually write this equation down and only that for number 10, because that's what it asks for. But again, you know, you can essentially, this can actually answer 8 and 9. Because 9 says select the power law trend line to fit your display equation. So again, this tells you how well you did. So you're answering the question, say, well, did I really, does my data really show that I can model E proportional R to negative second? Yeah, indeed it does. Negative 2.037 is pretty close to negative 2. So yeah, you're you know, if it was like negative 2.2, I'd say, well, I don't think so. You know, there's something not right with your data, or maybe this is not the right theory. No, this is agreement right here. This is agreement within, you know, you're in an exponent, and you're starting to disagree a little bit in the second decimal place. But again, this is you know, a touchy experiment where you do the experiment a couple times, you're going to get different answers, right? So this to me shows, yea, verily, that you are supporting Coulomb's assertion, Coulomb's law. Okay. Of course, in the table, little table on the bottom of page 3, I mean, all you'd write down is it wants you to kind of write down, you know, according to the form, what you think Coulomb's law ought to be, and let's give a value for K. All right, well, that's easy. So for continuing on number 10, again, let's even go further and try to evaluate K again. We evaluate K two different ways in the last experiment. Let's try to do it again here. So what Coulomb is predicting, the theoretical prediction on the left hand, again, we're looking at number 10, bottom of page 3. Coulomb is predicting that you should look like this: KQ over R squared. Again, I'm just looking at magnitudes. And so I want to try to write my formula that way. So what do I have? Well, my power law says, at least this is my power law, 9.0882 R to the negative 2.037. I mean, Excel called this X, but we know that's, I mean, Excel's going to call everything Y versus X, but we know Y in that Excel plot is E. We know the X in that Excel plot is R, right? So let's see, what does this look like? Well, as close as I can come to this is this. I can say, well, E is looking like, you know, well, my 9.0882 divided by R to the 2.037. That's as close as I can get. So what is this 9.0882? Oh, well, that's KQ. This is darn near R squared. I mean, it's with experimental error, but let me get an idea here. So this 9.0882 is what I'm calling KQ, 9.0882. And so what would K be? Well, K would be 9.0, and again, these are my numbers, 882 divided by what I call my source charge Q, or 9.0882, and my Q was magnitude-wise was 1.0 times 1 nanocoulomb, right? From 10 to the negative 9 coulombs. Well, that's really easy math there. That just tells me that my K value is going to simply be 9.0882 times 10 to the 9. Or my K value is 9.0882 times 10 to the 9th Newton meters squared per Coulomb squared. And again, that's pretty close to 8.99 times 10 to the 9th. So again, another pretty good agreement with the real value of K. That's the value that I got from this experiment. But that's a really good agreement compared to what the actual value is. And in fact, I probably could do a percent difference at this point. I'm sorry, not percent difference, but a percent error, because I actually have a scientifically accepted K value. So I mean, you don't really have to do that. But again, again, you're getting a value K. It doesn't ask you how accurate it is. I mean, if it asked you how accurate it was, then you would want to do a percent. I say percent error at that time because you would, as I said, you have a scientific accepted value. Okay, I'm on the top of page 4. There's one more number here regarding part 1 for point charges. Remove the positive charge and place a 1 nanocoulomb negative blue color charge at the same place. What difference and what is the same about the electric field due to a 1 nanocoulomb negative charge compared to that 1 nanocoulomb positive charge? So again, real easy on this. I mean, so what we've been playing all along with the 1 nanocoulomb positive charge. Well, you can kind of imagine what would happen. I've already kind of said it a few times, but again, don't believe me until you do an experiment. And so we do the experiment. So let's go and share again. And all we're going to do here is simply put the positive 1 nanocoulomb charge back in the toolbox. Okay, electric field went away, and stick a negative 1 nanocoulomb charge there instead. And as we would expect, the electric field lines are radially inward. The magnitude is bigger the closer you are to the point, the source charge of interest, and smaller further away. And so again, I would say something like the electric field vector magnitudes are the same, but its directions are reversed. And you want me to compare what I showed before? Well, it looks really the same. It looks like deja vu, except all the electric field vectors are radially inward instead of radially outward. Okay. That completes part 1. Any questions about part 1? So, I mean, it's pretty cool stuff, but but not too difficult. Okay, so I'm going to start part 2. So I'm just gonna hit the reset button. Now, part 2, let's kind of do a little theory here real quick. We don't actually talk about this in the class, and it's a shame. I think you do in OpenStax, but the concept of a dipole moment, as it's called, is very important. Now, when you're talking about electric distributions, all right, we have to kind of, so in general, we're talking about the easiest possible electric charge distribution of interest, and that's the point charge. So in general, electric charge distributions are complex. And there's a nice way in physics is where you add up what are called, you basically have, you have some charges you can kind of consider being by themselves, other charges that are maybe more like paired, what we call a dipole. Other charges, maybe you might get 4 of them together, we might call that a quadrupole. And you might get a clump of 8 somehow, some way, called an octupole. And essentially what you end up doing is your charge can end up looking like monopole contribution. I mean, single charge, like we've been talking about, plus a dipole contribution. And this goes more in advanced physics. Plus, okay, so we have 1, 2, we go to 4, quadrupole contribution, plus an octupole, so 1, 2, 4, now we go to 8, octupole. I think that's how you spell it. So on and so forth. When you're building up a general charge distribution, one way to look at it is add up all the single charges, the ones that kind of just want to be by themselves, or the ones that end up, by themselves, single, the monopoles, mono meaning one, and then the ones that are paired up, plus minus are paired up, like maybe like a carbon monoxide molecule, as Dr. Edmonds gives as an example, or maybe like a water molecule has a positive end and a negative end. You can think of it as a dipole. And then you have certain situations where you have 4 charges that are together, 2 pluses, 2 minuses, that kind of interact together as a unit. We call that a quadrupole. Octupole would be 4 positives, 4 negatives, or 8 that work together as a unit. They're always doubled. All right. Now, you get into more graduate level or even an advanced undergraduate electromagnetic theory, you're going to go through all of these. We do monopole, dipole, quadrupole, octupole moments. They're called moments, basically. Well, in this particular case, we're going to cut off at dipole in this class. And so there's something that's really interesting about that is that electric charge actually has a monopole, right? Magnetic fields, one of the things we're going to understand from magnetic fields is that when we talk about magnetism, there is no such thing as a magnetic monopole. You can look for one until the end of the world. No one's ever discovered one. So no magnetic monopoles exist. Right? So basically there is no such thing as magnetic charge. And we'll talk more about this when we get into, I guess, chapter 22 or so. But in magnetism, you always have North Pole and a South Pole at a minimum. So if I take a magnet, for instance, again, this kind of appears ahead, but it's a very important concept. You take a magnet and say, okay, I get it. I have a magnet that has a North Pole and a South Pole bar magnet. Why? You know what? I'm intent on separating a North Pole from itself. So I'm going to cut this magnet in half. Well, you cut the magnet in half, and all you've done is create 2 magnets. Each one of them has a North Pole and a South Pole. And you can dice up this magnet as much as you possibly want. You can get it down to the atomic level. Even an atom has what's called a magnetic dipole moment. Even an atom will have a North Pole and a South Pole. So there's nothing you can do about it. You'll never find a magnetic monopole. And so again, the idea is, we've been talking about electric charge. Well, hypothetically, an electric charge is what's called an electric monopole. All right, so there is no such thing as magnetic charge. So when we talk about electric dipole, that's the next level. Well, we have electric monopoles. I can separate charges out, right? So what electric dipole basically is, in the basic sense, it's Dr. Evans is a good example. Essentially, 2 closely associated charges. I may have a positive Q charge closely associated with a negative Q charge. And let's just say that the distance between these 2 charges, let's do it this way. I have 2 charges, plus Q and minus Q. And we can imagine there being a vector from the negative to the positive. We call this vector P. And the distance between these two charges, these closely associated charges, is also a vector. That's your displacement. And so you define an electric dipole. In this way, you have separated charge Q. You define electric dipole as P. Again, another use of the letter P. Do not know why they want to use P. We already use it for momentum, and we use it for pressure and power, and now we use it for electric dipole moment. But it is what it is. But it's given as essentially this separated charge Q times S. Simple that. It is a vector. It's a vector that would be drawn from the negative charge to the positive charge. So Dr. Edmonds gives an example of carbon monoxide. Carbon monoxide, if you look at it, it's just CO. And the C, you can think of it as a positive, and the O, you can think of it as a negative, and together they form electric dipole. Water is another example. So water is nice. Now you have H2O, right? So for water, you have the oxygen molecule. We know this atom very well because we know that each of the hydrogens, there's a 180-degree angle between them. So this is a molecule for obvious reasons that we know very, very well. It is polar in that it has basically a negative 2e overall charge on one side of it and an overall positive 2e charge on the other side. So water is highly polar. You know, you put water in a test tube, or you put water in a graduated cylinder, for instance. You notice that water, you know, let's say I have a little graduated cylinder, water just doesn't sit there like this, right? It does not sit there straight across. We know that water has what's called a meniscus. You go to your chemistry, water gets attracted. I mean, I'm being very deliberate here, but it's like a little smile. Water it's pulled up on each side to the glass because it is a polar molecule. It is attracted to the glass, so water is very polar. That's why when you have as I discussed in the chapter 19 video, you know, I discuss capacitors and, you know, putting a material between them called a dielectric. Well, water isn't. I mean, if you can make it work, water would be probably one of the best choices of a dielectric. It is highly, highly polar. It has a very high dielectric constant, you know, because it is so polar, right? And so there's a lot of things that we can actually describe as dipoles. And so one of the things that you want to try to do is we want to study these dipoles. We're going to find out there's a really interesting electric field around a dipole. I mean, it's much more complicated than just a simple radially outward or radially inward monopole moment. But when you have a dipole, you notice that the electric field becomes more complicated and actually very beautiful. All right, and so on the bottom of page 4, we want to kind of map out how we would draw a dipole. And of course, I want to do things as simple as possible. So number 12, it says, all right, now we will examine electric field of a dipole. The magnitude and direction of the electric field depends on the distance and the direction. We will investigate in detail with two directions. The charges available in the simulation that how you create a dipole moment is 1 times 10 negative 3, 1 times 10 negative 9. Okay, now I corrected Dr. Edmonds on this. When I look at this the first time, reading carefully, I see this as 1 times 10 negative 9. When I see cm, it looks like centimeters to me. But let's be careful. Remember, it's talking about a dipole. So it's really QS, Coulomb meter. So this really ought to say, and I corrected the lab and sent it back to them, but it should be capital C with little dot, little m. Coulomb meter. I mean, the way he wrote it out looks like centimeters, and I was like, oh, that's not. But you know, but it's really a dipole moment. A dipole would be Coulomb meter. So when you see this 1 times 10 negative 9 cm, it's really Coulomb meter. That's what you want to try to make. You're going to try to make that kind of dipole. And with the direction of the dipole moment pointing to the right. Okay, so we want to make that. So look back in the figure at the top of the page and make sure you determine the direction of the dipole moment carefully or correctly. Make a sketch below. So all I really want to do is say, okay, well, what I'm after is I have my grid. All I really want to do is imagine that I have this. Again, before you build a house, you want to make a blueprint, right? And so before I go off and make, draw a grid and drop down dipoles, I mean, anything you do in life, you want to make a plan. You go on a trip someplace, a road trip, you don't just get on the road, well, we're going to go head to Houston. No, I mean, unless you've been there 100 times, you want to go on the road and you want to make a plan like, okay, how am I going to get there? Where am I going to go? Do I have alternate routes in case, I run into some bad weather, kind of thing, right? And so let's kind of make our plan here. So we want to try to make a dipole that's about P is 1.0 times 10 to the negative 9 Coulomb meters. Okay, it's going to be really easy. Don't worry. So in my plan, I want to separate a charge Q and negative Q. Negative Q, I want to draw it to the right in Q. I want to take one of those major distances that's a 1 meter across. I want to take a distance that's 1 meter across in my grid, place my Qs, that way, and consider, again, my dipole is going to go from the negative to the positive. That's my P. All right, and I want to consider what value. How do I draw this? I don't even know this yet, right? All I know so far is that that's the PM after. All right, and so okay, that's Coulomb meter. So and all I have at my fingertips is a negative or positive 1 nanocoulomb charge. So if I know this, I say, okay, well, simple math here. P is QS. And I got to figure out how far apart I draw these charges. I kind of gave you the answer. I was being a little sloppy here. Well, I know P and I know Q. So S is simply going to be P over Q. Or 1.0 times 10 to the negative 9 Coulomb meter divided by 1.0 times 10 to the negative 9 coulombs. And so my S, I got to draw it apart to be 1 meter. So I'm going to draw. All right, so that's my planning. I want to draw it so it's the dipole's to the right. That means the negative is on the left, the positive's on the right. How far apart do I put my little charge? I mean, the only options I have are a 1 or negative 1 nanocoulomb charge. That's all I have at my fingertips. So I don't have, there's other ways you can do this. You can just draw straight up, or there's other ways you can do it, right? But I want to just go to the right, and I'm just going to drop it so that it's 1 meter down. So I'll put this on my grid, a 1 meter over, put a positive charge on there. That's my dipole. That's how I make this happen on my grid. And so this is really this little grid on your the bottom of page 4 is nothing more than just planning. So on your grid, you'll draw this. And where do I want my origin to be? Well, the origin is always going to be midway between the dipoles. This is your origin. That's your 0, 0, if you will. So when you start measuring you're going to be measuring from the origin. All right. So when you say, I want to consider R equaling 1 meter away. Well, it's going to be 1 meter from the center point of that dipole. Your origin is at the center point. So again, the origin of a dipole is at the center. It's at the center. That's where the origin is. So you make all your measurements, it's going to be from that center point. So if this is a meter across, it means it's going to be half a meter here and a half a meter there. So it's going to be one of your minor grid points, if you will. All right. So that's my planning. It told me here, it wants me to tell you where the origin is too. So all this information, all this stuff should be right around the bottom of page 4. Okay, that's your planning that you did. Now you turn to page 5, which is basically number 13, and you start laying stuff down. So we go back to the software. So okay, well, I know how to make my dipole now. So now let's go off and just make it. Any questions right now? All right, let me share with you. So I have a blank palette again. All right, so the first thing I want to do, of course, is, I hit the reset, right? So I want grid, and I want values. Again, I kind of already know what the values are, but again, I want to know it anyways. All right, so what am I going to do? Well, I'm going to pick a spot. Let's just kind of pick, I don't know, I want to be a meter apart. So I want the negative on the left, positive on the right. So I'll maybe pick someplace like maybe, well, not there. My mouse is getting a little crazy. Sorry about that. I'm going to stick it like right, trying to plan. So I know I'm going to lay down a point here. Okay, so there is a single negative point charge. Trying to be careful here. It's really hard to lay it down just right. All right, and then the idea is I'm going to put a positive 1 nanocoulomb charge just to the right, but it's going to be 1 meter away. Now I have this very beautiful arrangement. So that is more complicated than, say, let me kind of give you more of a better feel. Move these kind of a little further up. This is more complicated than just, say, a single point charge. All right, so that is the electric field around a dipole. That's essentially both of these charges are plus or minus 1 nanocoulomb. The dipole moment would be going from left to right, as I predicted it would be, and they're 1 meter apart because I want the dipole moment P to be 1.0 times 10 to the negative 9 Coulomb meter. So that's what I get when I do that. All right, so let's see, is that what number 13 tells me to do? On your drawing, and okay, it's figure 12, but mark the center. Okay, once the center where the dipole is, pick a point to the right of the charges and mark it as P1. At that point, draw vectors represent the electric field contributions from each of the individual charges in your dipole. So I didn't do that. I apologize. So sorry, let me go back to my board real quick. So I forgot one little thing. I didn't turn my page on my diagram. So I already have my origin, right? So on my diagram, I just have to pick a point out to the side, to the right, and kind of make a determination of what I think that point looks like, what the electric field looks like. So if I pick a spot to the right, say out here somewhere, well, the positive Q is going to effectively give me a rightward, directly to the right, positive X hat electric field. The negative is going to pull me in. However, the negative is further away. It's going to have a weaker effect. Why? Because remember Coulomb's law is electric field is K Q over R squared. So it's further away. So it's going to be weaker because it's one of our R squared contributions. So it's going to be a big push to the right, but it's a traction a little bit. So overall, at that location, I should still see an electric field directly to the right. Not as big as if it was just the positive point charge itself. The positive point charge, remember, electric fields add via superposition. So you have the contribution from the positive Q, but then you have the contribution from the negative Q. But that subtraction is not as big. So there's going to be an overall rightward electric field. That's what I predict. If I take a point directly to the right of that dipole, I expect electric field to be positive and to the right. So let's see if I'm right. So let's go back to this. So that's all number 13 is asking us to do. So number 14 says, now reproduce a dipole on your grid in the simulation, making sure that the dipole moment is directed to the right, which we did already. And the magnitude of the dipole moment is 1 times 10 to the negative 9 Coulomb meters, which we also did. Make the center of your dipole be the origin. So he's repeating himself. All right. So let's go share the screen again. And let's see what happens. So here we go. And I'm just going to pick a spot to the right. So my origin is right between the negative and positive charges. and I'm gonna take my sensor and I'm gonna kind of sample a location kind of off to the right as I was asked to. And let's see, I predict I should have electric field line going to the right, and I didn't line it up perfectly, but there you are. It's not as long as it would be if it was just a positive charge by itself. But overall, that would be what I would expect to see, you know, for a location to the right of this dipole. So it's exactly what I wrote on the board. All right, so what we're gonna do now is we're gonna take some data. So number 15 just says, okay, let's make sure measurements of E at a series of points along the x-axis to the right of the dipole. Again, I'm going to call that positive x hat. I'm going to call straight up negative positive y hat. All right. So so essentially in your table, you're being asked, you're saying, okay, x is 0, x is 1, y is 0, x is 2, y is 0. Basically, all that means is you're just basically sampling points along the positive x-axis. And again, 1 means what? Let's see, it's not what I've drawn here. So if my smallest value of x is 1, that value would be actually right here. Why is that? Because again, it's from the origin. The origin is where we measure from the dipole. Locations from the dipole are measured from the origin. They're measured from the center between the dipole. All right, so that'll be right here, right between the minus and plus. So you wanted me to be 1 away to the right. Well, here is 1 unit, that's a half, plus another half is 1. So in accordance with, you know, the legend on the bottom right, that's 1 meter away. And so I would write down, if I was you, if I was doing this experiment, I'd write 31.0 volts per meter as my first data point. And again, what direction? I would say positive x hat. I drew a little orientation. I drew a little Cartesian. I said to the right is positive x hat, and upward would be positive y hat. I'll redraw the orientation in a moment. But anyway, that's what I would say. I would say as my first answer. Let me stop sharing for a minute. Go back to my whiteboard. So my first answer in that grid would look like the following. In accordance to, again, you do this experiment 10 times, you'll get 10 different numbers. But for my grid point, what did we see? Well, we saw X in meters. We have this whole table. We have Y in meters. We have electric field. Again, everything should be in SI. This is for Coulomb. And we have direction. Off to the side, I wrote down my orientation, which is going to be positive x hat to the right, positive y hat up, negative y hat down, negative x hat to the left. So I can actually speak in terms of these unit vectors. And so what would I say? Well, on that first row, according to what I just got to showing you, I say 1, 0. They gave that for you. What did I say? What was it? 31.0 volts per meter, newtons per coulomb, whatever we want. What's my direction? Well, plus x hat just means to the right, right? And so I put that down as my first data. Take another data point. I'll do another one for you. Show my screen again. So that is for 1 meter away. The next data point, we want 1.5 meters. So I take my little test sensor here and I move it out to 1.5. Again, still pointing to the right, 6.66 volts per meter. All right, that'll be my next one. So my second row would read 1.5 for X, 0 for Y, 6.66 for E, and positive x hat for direction. Do another one. Again, I want you to do these yourself. You notice that the vector is getting smaller and smaller. 2.54 volts per meter would be like this. So maybe my third row might read something like this: 2 for X, 2 meters for X, 0 meters for Y, 2.54 newtons per coulomb for the electric field, and positive x hat for, again, the direction. And then what I want you to, you can do the next two yourself, but 16 then says, okay, plot the measured dipole electric field strength versus R. So now we're going to plot E versus R. Which electric field, single point or dipole, drops off more with distance? Use electric field graphs as support to explain your answer. So again, you always want to explain yourself via data. So let me go to my Excel spreadsheet again. Any questions about what I just did so far? I'm on number 6. I'm just on number 16 on page 5 now. All right, I'm going to stop sharing. Okay, let me go to my Excel again. I'm going to go to my different data now that I did earlier. Let me share this. Share. Here we go. All right. So there you are. So again, this is what I took, threw it in Excel. I made a new tab. I call it Data Part 2. And again, I did the same thing as I normally do. I highlight the two columns. That's not what I want to do. All right, try this again. My mouse is being goofy. Could be the Zoom is being goofy. All right. So normally, how do you do it again? Again, you know, I'm just kind of giving the quickie little Excel lessons. Again, you go highlight it, select the scatter plot. There you go. And you notice it looks like some sort of a decaying behavior again. And you go through the whole same situation, changing your fonts, putting in a title, putting in your axes, so on and so forth. But you'll notice that, and then you'll also do a power trend line. So I did all that earlier. I have a tab I called electric E versus R for dipole. And so you bring that up, and I get something that looks like this. And I look at it and say, okay, well, interesting. So I have Y equals. So I did the trend line. I chose power again, and I'm seeing that Y is some number 29.95, X to the negative 3.469. Wow. All right. Well, that's definitely not a 1 over R squared. So that's like a E is, you know, that's like a proportional to a R to the negative 3.5 or so. I mean, so what that's telling you is that's your evidence that the curve or the electric field that falls off faster is this one, the dipole. The previous electric field is falling off as 1 over R squared. This electric field is falling off as 1 over R to the 3.5 roughly. So you're plotting the measure, you're answering the mail by plotting your, number 16 by plot the measured electric dipole strength versus R. Well, there it is. Which electric field, single charge or double, or dipole, drops off more with distance? Use electric field graphs to support your answer. So I would use this graph, and I would maybe say something like this. I mean, again, you want to support your answer. You just want to say, oh, well, electric dipole. That's not good enough. You want to say electric dipole and why. You want evidence. I might say something like this. I mean, again, you want to give complete answers, and this is a professional document. So I might say something like the electric field E. What am I? 16. Again, you have your graph, right? I just showed. So we got that. So you'll include that, right? So that's just something you include. But I would say something like this: the electric field. Again, you use your own words, but this is how you'd answer a scientific inquiry. Electric field E versus radial distance I'll just say magnitude. R from the center of the dipole, or the plot of electric field E versus radial distance R from the center of the dipole is attached. All right, so it's attached, so I'll go off looking for it. Its power trend line is I mean, again, you're going to have different numbers than me. But I got something like 29.95 R to negative 3.496. All right. Hence, it decays much faster than the E proportional to R to the negative 2 for the point charge. Something like that. So I had said something like the plot of electric field. I mean, I give the graph, of course. I attach it, but a plot of electric field E versus radial distance R from the center of the dipole, again, that's where you're plotting. Tell me what you're doing, is attached. Its power trend line is equals 29.95 R to negative 3.496. That's how you got your data. You use Excel, okay, that's acceptable. And you use a trend line, that's acceptable. Hence, it decays much faster than the E to the negative R, E proportional to R to negative second for the point charge. I mean, again, that's what you're being asked. You don't just say, oh, well, it's the dipole. Well, tell me quantitatively how much so. Okay, and again, this kind of way of answering things is true for any, or not just physics, but any of your classes, right? All right, I'm hitting off to 17 now. Any questions so far? All right, 17 basically says, well, make some measurements of E at points along the x-axis to the left of the dipole. So what I would do is I would make a table just like you see in 15, and I would consider, so I'd make a table. So this is for 17. Again, you're looking for, all I've done so far is looked at along positive x. So 17, well, if it wants me to make a comparison, well, first thing I'll do is I'll make a little table, and my table will be like x in centimeters. I'm sorry, x in meters, y in meters, E in newtons per Coulomb, and direction. All right. And so I would do the following. I mean, again, I'm looking along the x-axis, so I'm going to have 5 data points. So 0, 0, 0, 0, 0. But I'm going to look at, well, okay, so let's see, the first one was 1. So let me look at negative 1. Let me reflect across the y-axis. Negative 1.5, negative 2, negative 2.5, negative 3, right? And I want to figure out, I want to basically just go back to the software, put my sensor in each of those places and see what it looks like. I think it'll surprise you what you might see. And so let's do it. So I'll do a few for you, but I think you'll see what I'm talking about here in a moment. So let's go back to the. So again, let's kind of take a look and see. We're looking for symmetry now. So I got done showing you. Let's see. Can I do this? 1, 1, and 2. 1, 1.5, 2, 2.5, 3. Yeah. I can do it. I have to make sure I drew it out far enough. So I'm going to go and I'm going to look at -1 now. So I'm going to try to move this slowly so I don't. All right, so oops, my internet connection's unstable. That's not good. All right. You guys hear me okay? Anybody?
So far, so good.
All right, good. I got a message that my internet connection's unstable, so that's never good. All right, so all right, so we look at, and I stick it now -1 from what? From the center. So again, everything is from the center of the dipole. 1/2, 1. So -1. And I know something peculiar. It's still pointing to the right, like it was before, and it's going to have a number that's really close to. I mean, I get 34.6, which is pretty close to what I had before. So that's a really close magnitude in the same direction, still positive x hat. If I go and test out, let's say -1.5, I rapidly get a smaller and smaller vector. And now I'm getting, oops, that's not very good. Like 7.07. I mean, roughly about the same magnitude, still to the positive x hat. If I go and try one more time, let's go -2. And again, I'll get about 2.7, 2.69, roughly about the same one. So I'm noticing here, again, there's gonna be some error, but you'll notice that what I noticed is that when I test points along the x-axis in the other direction, I get about the same electric field magnitude, and I also get directions that are all positive x hat still. All right, and so in that case, I mean, that's and really what's happening here is that the negative charge is attracting more and the positive charge is repelling less. That's why that's happening on the other side. Again, we're talking about imagining a positive test charge. All right, and so I would say something to the effect in words describing that the magnitude's about the same. And again, look at it carefully. The direction is still positive x hat according to this setup. You might choose to set up your direction differently. I mean, well, I think he asked us to set it to the right. So anyway, so again, a little verbal description in 17. All right, going back, we're getting close to being done here. So going back to number 18, or going to number 18, I'm on page 6. Let me stop sharing here and let me go back to the whiteboard once more. Okay. Let's make another prediction, which is kind of interesting. So it says here, okay, on your drawing on page 12. So we're going to go back to the original drawing on page 12, the first drawing. Pick a point above the center of the dipole and mark it P2. At that point, drop vectors represent the electric field contributions from each of the individual charges in your dipole. Each electric field vector should be drawn with its tail at P2. Also draw a vector to represent the net electric field produced by all the charges in the dipole. So again, what's the dipole look like? Going back to the very first part of the dipole experiment, and that would be that. So you go back to the drawing on the bottom of page 4. We essentially had a negative Q and a positive Q in close association. We know the dipole is going to come across, that's P, and we also know that this is my origin. Now I'm being asked the following question. Let's pick a point along the vertical. Where do I think the electric field is going to go? So let's see here. Let's pick a point here. some point. Now, if I imagine there being a positive test charge at that location, I would expect there to be repulsion here. I would expect there to be some electric field that direction. I would say coming off, I'll call this E plus, coming from the positive charge. And then I would expect attraction of a positive test charge with the negative. And again, these forces all connect line, center to center. And I would expect, again, I'm calling this P2. That's what they told me to do. And I would draw that vector, try to draw about the same size right there. I'll call that E minus. Now, if I drew my vectors right, I should see that the vertical component should cancel out when I add the two vectors together. Their horizontal component should add. The cosine, they should add. So I should see overall, my overall vector E should be all to the left. So again, E should be what I'm calling E from the positive charge plus E from the negative charge. I mean, again, this is just simple little analysis, but if I stuck my sensor right up there along Y, that's what I should actually see. So I should notate that also on that diagram. And I'm just kind of, before you go off and do something, let's kind of make a plan, right? And so that's what I expect to see. Let's see what reality is. So again, I'm on the top. So I could put a little check mark on number 18. I did it. 19. So let's go off and do the same kind of thing. We're going to fill up a table and share my screen again. All right. So using the same dipoles before, what I'm going to do is I want to consider going along. So every x is going to be 0. That means I'm going to be going along a y direction. So I'll go half a meter up. Okay, well, this is the origin. So here is a half a meter. So let's try to put it there without going crazy. Something like that. But a little bit better. Oh, sorry. Come on. All right. I don't know why this thing is. My mouse has gone nuts. All right. And that's probably about as good as it's going to get. If I touch it again, it's going to. Anyway, you see, that's what I predicted. And so you could probably do a better job than I did there. But, what would I write down on my table? Well, I might write something like, well, I think I can do a better job. That's not centered very well. There you go. So something like, for that first row, x is 0, y is 0.5. Maybe, my E would be, according to here, would be 27.6. And notice that it's predicting like I thought. It's my direction would be what? It'd be negative x hat, according to my orientation. Negative x hat would be the direction. And then the next one, we'd say, okay, well, let's try 1.0. Again, I know it's 0.5 because it's from the origin. Here's the origin right in between the two charges. Here's 0.5. 1 goes a little higher. Again, my electric field is still, overall electric field is still to the left, still negative x hat. Now it's like what, 6.57. 1.5. I just keep moving it out. I might actually have to move my charges down. So you might actually, for this experiment, you may have to actually move your charges down because you may not get to 3, right? So again, you might have to experiment and do that. You might, that's why I was trying to be careful about where I put my charges. So again, you do that for, for 19. Doesn't require you to make a table. Now for 20, you would draw your own table, and what would you do? Well, you would basically sample the negatives. So you go right back down here. It's big again, right through the center, and then here's negative 0.5. And something that's interesting, you'll see again another symmetry. You'll notice that, well, it looks pretty much just like the measurement of positive 0.5, oh, sorry, positive y equals 0.5. And you'll notice that at y equals -1, symmetry-wise, it's negative x hat axis, and it looks very similar to the value at for y equals +1, and so on and so forth. You notice that there's this symmetry. So again, I'd write that diagram and maybe say, well, compared with each point considered in number 19, each corresponding point reflected about the horizontal axis had electric field lines of the same magnitude and direction, for instance. So again, you know, kind of map out what you see in 19 and 20. You're kind of doing what Coulomb did. All right, the last page is just an overall summary of what you saw. So I'll just read it, what I did. I mean, 21, summarize what you observe about the magnitude and direction of the electric field from a single point charge. In particular, how this electric field depends on distance from the point charge. Well, I wrote down what I saw. I said something like the magnitude of the electric field of a point charge is directly proportional to the magnitude of the source charge and inversely proportional to the square of the distance from the center of the point charge source, or center of the source. At least, let me read it again. The magnitude of the electric field of a point charge is directly proportional to the magnitude of the source charge and inversely proportional to the square of the distance from the center of the source point charge. So again, that's what I saw. The direction electric field is radially outward for a positive source charge and radially inward for a negative source point charge. That's what I saw. So summarize everything that you saw about your experience where the source charge was a point charge, a positive, you know, whatever it was, you know, I guess positive one nanocoulomb. 22 is going to summarize everything you saw when your source charge distribution was a dipole. Right now we're going to this is our very first ever charge distribution, the electric dipole. So in words to summarize what you observed is number 22, last problem, last page. Summarize what you observe about the magnitude and direction of the electric field from a dipole. In particular, how does it depend on the distance and direction from the center of the dipole? Again, everything again is from the center of the dipole. I said something like data analysis showed that the magnitude of the electric field from the center of the point charge is directly proportional to the separated charge. I'm sorry. One second. Data analysis showed that the magnitude of the electric field from the center of the dipole is directly proportional to the separated charge in the dipole. However, its power r is on the order of r to the -3.5. If the negative to positive direction of the electric dipole is along the positive x hat axis, as in the case demonstrated in this write-up, then the direction of electric field along the x-axis to the left or to the right of the dipole is along the positive x hat direction. For any point directly above or below the center of the dipole along the y-axis, the electric field points in the negative x hat direction. Again, summarizing everything that we saw. You know, it's kind of interesting, you know, this configure, you know, what the electric field looks like, and you know, maybe you might guess one thing or another, but you know, if you move the if you analyze a point anywhere along the x-axis outside of the dipole, it's going to be electric field to the right, you know, along the dipole. If you analyze along the vertical from the above or below the origin of your dipole or center of your dipole, it's always going to be in the negative x hat direction. So who would know? I mean, again, you know this from experimenting, and you can actually predict it theoretically, as we did. So again, kind of summarize everything, and in my little write-up, I included two plots. I included the electric field, the point charge, basically E versus R for the point charge. And I included what I would turn into my professor, electric field to electric dipole versus R for the dipole. So again, that's what those. So you should have two plots that you're also turning in. E versus R for the point charge, E versus R for the electric dipole. That's all I have for the experiment. Any questions? I had no trouble firing this experiment up, so it shouldn't be. I mean, and so far this software has been working pretty well this semester. You guys still with me?
Yeah, I haven't had a problem with anything either.
Huh?
I said I haven't had trouble with the software either. It's been working well.
Awesome. Yeah. When we get toward the end of this class, they start using Java more, and we're gonna have some more. I think they improved some of the software, but when I taught this class in the spring, we're starting to play with the simulations, and they kind of thought, well, let's get smarter and let's go use Java more, and then gets to a point where if you have an Apple machine, you're going to have a hard time with using Java, and you need a PC, and then you need to go through the whole process. I actually had to write University of Boulder or University of Colorado and ask them, how in the world I make this work, and they kind of give me a how-to. So toward the end of the spring semester, I ended up kind of just doing experiments for people because they just couldn't bring it up, and it's just easier if I just did the whole thing, and we had a common set of data. Worst case scenario, if we have trouble with one of these labs, I'll do that, but I'm kind of hoping that you guys kind of play with this. I mean, you really ought to be touching stuff in the lab, but you know how it is with COVID. Anybody else? Nobody? Well, if you have no more questions, I guess we call it a done deal. Last week's lab is due this Friday. Homework should have been turned in by yesterday. So, and again, this is chapter 19 week, so there are chapter 19 lecture videos available to you.
Thanks, Professor. Have a good night.
You too. Take care. Anybody else? Hope these sessions are helpful. All right. See you guys later.